If some of you could turn on your video so I can see some of your faces, so I feel like I'm not just talking to the wall in front of me. Thank you. All right. So what are we going to be doing now? So this part of the course, which is the third part of the course, the third and last part, is dealing with number one, probability. We're going to learn a little bit of probability today. And then we're going to learn how to apply it in different situations, which will be the final part of the course. And we use a fancy word for this application of probability. We call it inference, which means to take information about a sample or a small group of people and apply it or interpret it for the entire population. So we're going to be using a special type of software program called StatKey, which is free and available on the internet. And we're going to be using that instead of the typical statistical formulas that people learn in a regular statistics course. It'll be easy to use. You'll learn how to use it and learn how to interpret it. And so that's pretty much what will happen in the next month before we have our final exam. Now we have a third exam, of course, for this third part of the course. I think we've had 5 quizzes so far. We'll have our 6th quiz next Tuesday, which will cover what we covered this week. So there's no quiz this week. And I guess that's it for now. Any questions about our upcoming schedule?
When will our tests be graded?
They've been graded. I haven't updated the grades.
Yeah, that's what I mean. Like, you know how you add those extra points on there?
Yeah, I will be adding those extra points in the next few days. So no worries about that. It only takes me, half hour to update everybody's. So just need to find that half hour this week and it'll be done by the end of the week. Don't worry about that. So you'll know exactly where you stand. All right. Any other concerns or questions?
Okay. Extra points are like the 10 extra points that you're talking about, right?
Yeah. So the way it works is, I've been getting some questions about it. The extra points are there so that you score a little bit higher than you would have. So those 10 extra points. So for example, if you scored, let's say a 75, let's say you scored a 75 on this last test. If it was out of 100 points, you would have scored a 65. All right, so there's 10 points extra, just increase your grade. And then what I do is I add enough extra credit points as far as Canvas is concerned so that the percentage comes out to 75%. Because Canvas doesn't do overall grade based on points, it does it on percentage. So I simply multiply your score by 10% and add those points in, and then that divided by 110 gives you the correct percentage. All right. So that's.
Say that again, please.
Yeah. So what I do is I take your score and multiply it by 0.1, 10%, and then I add that to your score, and then that result divided by 110 gives you the correct percentage. So if you scored a 75, I want to make sure that you get 75% showing up on Canvas. So what I do is I add 10% of your score. For example, if it's 75, I would have added 7.5 points, make it an 82.5, and 82.5 divided by 110 is 75%. So that way that 75 shows up as the correct percentage when you do the overall grade. All right, so that's what the adjustment is, what I do so that your grade is correct. Okay, so that's what all professors should do. I don't know if they all do it because not all professors are math oriented, but that's the correct way of adjusting your grade. All right, but in essence, you would have scored 10 points lower if I had graded it out of 100 points instead of out of 110. So that's where the extra 10 points comes in. All right, in terms of a real score of 75 instead of getting a 65. And you also have to remember many professors have passing is 60, and my passing grade is lower than that, closer to 50. Okay, so overall, you're getting extra credit, and your grades are reflected in that. So you're fortunate to be taking this class with me, because I do know other professors who are more hard line in terms of grading. They will not go below 60 for passing, and they will not go above 100 for your tests. All right. So they're more hard line, and they don't give out extra credit either. So you really have to, do much better in those courses to get your passing grade. All right. So it looks like people are still coming in. All right. Any other questions about that? So today we're going to be covering chapter 14, which is called Understanding Probability and Long-Term Expectations. Now, some of you may be somewhat familiar with probability, and maybe some of you are not. But again, don't worry, because this textbook doesn't go into it in great detail. There are some problems that I will go over at the end of today's session, which will be the types of problems that you'll solve using your calculator. But it's not an advanced course in probability. There's many more rules that you would take if you were taking a regular statistics course than what you'll be learning here. But these are very basic, some basic rules, which will be used throughout the rest of the course. Right? Now, you were exposed to some aspects of probability when we were looking at those contingency tables. Remember those when we were looking at risk and odds, and relative risk and relative odds, or odds ratios. That's a little bit of probability there. But you'll learn some of the rules today, which are easy to apply. I mean, it's really what you're going to be doing from this chapter is just some very basic arithmetic. It's just arithmetic, not even algebra. So just follow along and you should be fine. All right. And again, look at the examples I do, which I posted. Look at the examples I've done at the back of the chapter, and those are the types of questions that you should be familiar with. All right, so let's go to chapter 14. All right. So here's your very first thought question. We have two different queries or questions about probability. Number one, or part A here, is if you flip a coin and you do it fairly, which means if the coin is fair, what is the probability that it will land heads up? I guess that most of you would know the answer to this. What would be the answer to this?
Would that be 50%?
Yes, 1/2, 50%, 0.5, however you want to express it, because there's only two possibilities, right? Heads and tails. So if it's a fair coin, it would be equally likely it would come up heads as it would come up tails. So probability that it would come up heads would be 1/2, 50%. Right. What is the probability that you will eventually own a home? That is, how likely do you think it is? Maybe within the next 5 years or so.
So you can't really provide an answer for that, because everybody's circumstances are different, and it's also not giving you enough information. So the first one is easier to provide a precise answer.
Right. So you're coming up with the idea that there are certain probabilities that are easy to calculate, and there's others that are harder. It wouldn't stop a person from guessing what the probability is of owning a home, right? Based on their circumstances, they could do that. But it would, like you said, many people will come up with different answers, right? Based on their individual circumstances. So these are two different types of probability. That's really what they're referring to here. That's very good. So explain what it means for someone to say that the probability of his or her eventually owning a home is 70%. How would you explain that? I mean, other than just saying that, is there an explanation for that? A little harder to figure that one out, right? Well, what one explanation would be is if you pick somebody at random, the probability that she actually owns a home is 70% chance. Or even a better explanation would be something like if we let's say selected a person over and over again for maybe 1,000 times, we would expect 70% of the people that we selected to actually own a home and 30% not to own a home. All right, so that's another explanation. It's sort of the proportion over the long term, the proportion of people who would actually own a home. So if somebody says 70% probability, that's what they're referring to, long-term expectation of the percentage of people who would actually own a home. All right, so I think that's hopefully helpful to you. Explain what's wrong with this partial answer to thought question number 1. All right, the probability that I will eventually own a home, or if any other particular event happens, is 1/2, because either it will happen or it won't. What's wrong with that reasoning? Well, again, using my explanation from the previous thing, right, about over the long term, you would expect 70%, if it's a 70% probability, 70% of the people to actually own a home. What they're saying here is 1/2, because either it will happen or it won't happen, but you're assuming what? You're assuming that it's equally likely that it will happen or it won't happen when you say 1/2, right? Flipping a coin, for example, it's equally likely you would get heads or tails. So in that case, 1/2 makes sense. But there are circumstances where the chance of something happening is not, and it not happening are not equally likely. Okay. Picture rolling a die, 6-sided die, right? Where you have 6 different possible numbers, right? There's dots, the number of dots, 1 through 6. All right. The chance of rolling a 2 out of the 6 is 1 out of 6. It's not, the chance of not rolling a 6 is 5 out of 6, because there's 5 other numbers. See what I'm saying? So the probability of an event happening and an event not happening do not have to be equally likely. And that's what this person here is assuming in their question here, in their answer, that it either will happen or won't happen. They're assuming that those 2 events are equally likely, and it's not always true. Any questions about that? Does that make sense? Why do you think insurance companies charge young men more than they do older men for automobile insurance, but charge older men more for life insurance? What do you think? Now, what does insurance do? You pay a premium, you pay some small amount of money, and then if an event happens, certain event happens, then the insurance company pays. Now, what's the type of event happens when you get automobile insurance? What type of event may happen if an auto insurance company would have to pay you money? What typically happens?
A car crash.
A car crash, right? An accident, some sort of accident. Now, why would an insurance company charge a young person, we'll say person, not necessarily man, a young person, more money for this insurance than an older person?
Can anybody answer?
They're typically less responsible with driving or don't have the
Right.
experience.
Right. So another way, go ahead. So somebody else is talking. Go ahead.
I said, and they're less experienced.
Yes. So what about the let's look at it from the viewpoint of probability. Which is the higher probability? That a young person gets into an accident or an older person gets into an accident, assuming all the things are equal. Basically, just looking at age, all right? We're not looking at, mental capacity or anything like that. How about just age?
Honestly, I don't really like this question because it's not necessarily true that a young person is going to get in an accident before an older person does. When we're younger, we tend to be more careful because we're like, I know personally for me, I was kind of scared to drive. So I was I was really like cautious when it came to driving. And I know old people who like go 100 miles per hour and don't care about the drivers around them. And, the more experienced drivers are the ones who do like the bull crap on roads.
Okay. All right.
So
Well-
I don't know how to really answer this without being like, a little biased because
Okay. So that's a good point that you're making, that sometimes it's the reverse, right? But what insurance companies actually rely on, Aaliyah, is actually statistics. So they actually look at the number of accidents and they look at age. And
but how often are they looking at these?
all the
Are they
time.
looking at them every year? They like
Every
renew
year.
it every year or
Every year. They look at it every year.
okay.
And actually they do it yearly because they want to base it on, they're not looking at, over 10 years. They're looking at it every year. And they base the premium based on that. So premiums will change based on the experience. They call it experience. The experience of what people are actually doing. So the insurance companies look at their drivers and see who are getting into accidents and what age they're in. Ages are actually a pretty influential result. And they do find typically with men, maybe not with so much as ladies, but certainly with men, that young men get into many more accidents than older men do. And yes, you're right, there are exceptions, right? It's not 100% that way, but insurance companies are in the business of statistics. They're looking at who is getting into accidents more, and obviously they don't want to. They want to charge those people, or they would like to charge those people more. Right now, there might be state laws that prevent that from happening, but the important point is that they would like to charge young men more because they get into more accidents. Now, that's the statistics. They're basing it off of what the actual reality. How about life insurance? Now, this one's easier. This one's easier. Maybe not as biased as Aaliyah was bringing up. Why would they charge more for an older person than for a younger?
Because you have when you're younger and you get life insurance, it's cheaper because you're like basically starting from like scratch. But when you're older, you have like a shorter lifespan.
Yeah, that's it.
So like that's why you pay more.
That's
Also,
it.
when you're a smoker or a diabetic or something, you're not able to have as much, like your life insurance can be like higher to an extent as well.
Right. There might be a different rate. Yeah. So you're absolutely right. It's, forgetting about these other factors that you just brought up, in terms of age, an older person would pay more because they have a higher probability of dying. And that's what life insurance pays on your death. So now, of course, there are exceptions, right? And years ago, maybe 150 years ago, 200 years ago, they did, there were companies out there who did insure, but because they didn't use probability, some of them were unlucky where somebody like died right away who was younger, or if they were insuring, cargo on a ship and it sunk, they would be out of business. They would be totally out of business before they even got started. So probability is very important for insurance companies to maintain their integrity. That means to be in business. And if you're going to get insured by an insurance company, you want to make sure that they exist when they actually need to pay out later, right? I mean, that's important. So yes, older person will be paying more for life insurance. All right. So good. All right. So you're getting the idea, and these are very good points that all of you are making. All right, and we have one more question here. How much would you be willing to pay for a ticket to a contest in which there was a 1% chance that you would win $500 and a 99% chance that you would win nothing? So how much would you, what's the most that you would pay? I'll rephrase the question. What is the most that you would pay for this game? A little harder question, right? Well, if I told you that your expected winnings, and I say expected because, you know, you haven't played the game yet. What you do is you take the probability and multiply it by the expected winnings. So there are two possible situations here. You either win or you don't win. What's the chance of winning? 1%. How much would you win? $500. What's the chance of losing? 99%. What's the, how much do you win? 0, right? So you multiply those and add them up. So 1% of 500 is $5, and 99% of 0 is 0. So you add up those numbers and you get $5. So $5 is the most that you would pay to be in this contest. That's how you would figure it out. All right. Most people don't know that, right? When they enter a contest, you know, somebody says you pay this amount and you do it, right, without thinking about it. But this is telling you the most that you should pay for this particular game, for this particular contest. So that's called expected winnings, expected winnings. All right, so let's talk a little bit about probability. What does it mean, and are there different interpretations? So probability deals with chance, right? Deals with an uncertain event. And we want to know basically what is the chance of something happening. And so it says here for the probability of winning a lottery based on buying a single ticket, we can actually determine that up front before you actually buy a lottery ticket. All right, because it's based, there's a certain type, this is a certain type of probability that it's easy to determine ahead of time. All right. Now, the other question that we are asked earlier, the probability that we would eventually buy a home, that's based on personal beliefs, right? Or life experience. Not all, but it's not like somebody had said, I think Aaliyah maybe said it. We don't know ahead of time what that probability is, and not everybody would agree on the same probability, right? Now, if you're playing a lottery, if you're calculating it correctly, everybody would agree that it would be the same probability of winning a single ticket, right? It would be the same exact probability for everybody. So what is this type of probability? Called the relative frequency interpretation of probability. It means that this is a situation where we can repeat the process or experiment, we call it experiment, over and over again, and we can come up with a calculation of what the probability is. All right, so that's called the relative frequency interpretation. All right, now this involves running an experiment, running it over and over again, and coming up with your probability. Okay. These are examples. You could buy a lottery ticket and observe whether it's a winner, and you keep buying them, and obviously most of them will be losers, but maybe occasionally you win. Commuting to work daily and observing whether a certain traffic signal is red or not. Testing individuals in a population and observing whether they carry a gene for a certain disease. Observing births and noting if the baby's male or female. These are repeatable events that we could sit down and take statistics, right? Just like we talked about with insurance companies, right? They will look at statistics and look at count the number of accidents and see what gender the person is or what age that they are. All right. So this is called the relative frequency interpretation of probability. something that we can run as an experiment over and over again. Now, what is long run relative frequency? It's the proportion of time it occurs over the long run. And sometimes we have these tables. Again, these are these contingency tables that we saw previously when we looked at risk. And the counts in here could be used to calculate these so-called long run relative frequencies. All right. So let's see what this says. It says the possible results for relative frequency of male births, weeks of watching. So we have 1 week, let's say we go to a hospital and we notice that there are 30 babies born that week and 12 of them are boys. So 12 divided by 30 is 0.4. We could look at a hospital for 4 weeks. And we could see that there's 100 births in that hospital over 4 weeks, and we notice 47 of the 100 are boys. Same thing over 12 weeks. Maybe there's 300 births that we're recording, and 160 of them are boys, like that. Okay, so you get the idea? So this is sort of a chart that counts the number of babies that are boys, and then we find the proportion of the babies that are boys. So we take the number of boys and divide by the number of babies. Notice when we get to 52 weeks, we've looked at 1,200 babies and 618 of them are boys. So notice the numbers here. They're getting, we start off 40%, but they don't have to be 40% after a week. It could have been 60%, right? But we notice that as the number of repetitions, number of babies increases, so the number of babies that we look at increase, we notice that the numbers get closer and closer to 50%. And actually, according to this, we'll notice that it seems to go closer to 51%. All right, so the percentage of babies that are born, according to this is way back in 1991, is about 51% in the long run. But as you run the experiment more and more, you'll get closer and closer to this long run probability of 51%. So the whole idea is that a long run relative frequency will give you the probability of a certain event occurring. Okay. All right. So how do we determine the probability of an outcome? All right. Well, using this relative frequency approach, we make an assumption about the physical world. For example, if we're using a coin, we're going to assume that it's equally likely that when we flip a coin, it comes up heads or tails. All right. So that's why we say the probability of a flipped coin being heads is 1/2. Now, if we ran this experiment, in other words, we flipped the coin 10 times, 100 times, 1,000 times, 1,000,000 times, we would find that the more we flip the coin, the closer the proportion of times that it would be heads would be closer and closer to 1/2. So the long-term relative frequency should be approach this 1/2 that we would expect, because flipping a fair coin should be 1/2 probability that it's heads. All right, so you get the idea? If we run the experiment over and over again, we'll get closer to what we expect to be the actual probability. Now, sometimes we don't know ahead of time when we run a relative frequency approach. We don't know ahead of time. We can't really guess ahead of time what the actual probability is. Like with the example of the proportion of accidents that are by younger people versus older people, that sort of thing. We may not know that ahead of time, but it's something that we can repeat over and over again, and we will end up with, if we repeat it enough, we'll end up with a estimate of the true probability. Okay. So this is relative frequency approach is a very good way, and this is what insurance companies use, the relative frequency approach for calculating probability. All right. So here's another example. Here's another method. observing the relative frequency. Well, this is the method we've been talking about. So here's, you observe the relative frequency of male births in a given city over the course of the year. And in 1987, for example, according to this, there was 3,809,394 live births in the US. And there was one out of those live births, 1,951,153 were males. If you divide those two numbers, you get 0.5122. So that's that close. That shows that it's close to that 51% number that we were talking about. Now, you may have thought ahead of time that it's equally likely that you have a male or female. It should be 50%, but it seems like if you use the relative frequency approach, you're getting closer, at least at that time, 51%. Maybe it's different now. Maybe if we did this now, maybe there would be more females than males. But the important point is this gives you an estimate of the true probability of an event, okay? The relative frequency approach. So how can we use this relative frequency approach? Well, it applies when a situation can be repeated numerous times and the outcome observed each time. Now, let's look at things like earthquakes or things that don't occur very often. It's harder to come up with the probability of an earthquake, isn't it? Because it's not something that can be repeated numerous times. All right, there's only a few earthquakes that occur every year, just a handful of them. The relative frequency should settle down to a constant value over the long run, and that is the true. We can estimate that to be the true probability of that event. Does not apply to situations where the outcome, one time is influenced by or influences the outcome the next time. Now, what do they mean by that? That means that the outcomes should be independent of one another. In other words, when we flip a coin twice, the second flip of the coin is not, the outcome is not influenced by what happened in the first flip of the coin. It's still going to be a 50% chance of getting heads the second time we flip the coin. And it doesn't matter whether we got heads or tails the first time. Those are called independent outcomes, all right? The first flip of the coin and the second flip of the coin are independent of one another. So if the outcomes are dependent on one another, then the relative frequency approach doesn't work. We have to find some other approach. All right, cannot be used to determine whether outcome will occur on a single occasion, but can be used to predict long-term proportion of times the outcome will occur. All right, so relative frequency approach is a long-term approach. Now, another way of looking at this fourth point here is if we say that, let me think of a good example. Maybe there's some reading program. We find over the long term, a reading program, the probability that a student over the long term will improve their reading through a reading program is 70%. Well, that doesn't mean that a particular student has a 70% chance of doing better in reading. Maybe that student with that reading program does 90% better, or maybe they don't do better at all. So we have to look at the relative frequency approach to probability is for a large proportion of people, not just for one person, all right? Does that make sense? I hope that makes sense to you. The other type of interpretation is called personal probability interpretation. Personal probability, which means that you're really just guessing at it based on what you believe is true. Maybe you're just it's a pure guess, or maybe you have some experience with it, but it's a guess. Now, here's the most important thing. Probability always is between 0 and 1. And so for personal probability, whatever you come up with must be between 0 and 1. Now, what does 0 represent in terms of probability? Anybody can guess what 0 probability means? Think about 0% chance.
No,
What does that
no
mean?
possibility.
No possibility. That's right. How about 1? 1 also means 100%. What does that mean? it means it will occur. No doubt about it. It's going to occur. Is there anything in life like that? Well, you might say, well, 100% chance that everybody will die, right? Eventually. So maybe you could say that. But most things you can't, right? Most things are in between impossible, which is 0, and absolutely certain, which is 1. So if you ever see a probability that's negative or greater than 1, you know it wasn't calculated correctly. It has to be between 0 and 1. So 0.1, 0.2, 0.3, 0.8, 0.9, those are all valid probabilities. Personal probability is basically, again, you're guessing, unless you run a relative frequency experiment, you're just guessing. You want to know what's the probability of finding a parking space downtown on Saturday? Well, you just sort of guess at it. The probability that a particular candidate for a position would fit the job the best. You don't know that till the person actually does the job, right? So it's a guess. These are all examples of personal probability. So, rules of probability. Again, this course, we're only dealing with the very basic rules. We're not dealing with all the rules, not even close. So the rules that are in this book are the only rules we'll be using. If there are only 2 possible outcomes in an uncertain situations, then their probabilities must add up to 1. This hopefully makes sense to you, right? If there's only 2 possible outcomes, the probability of one or the other outcome occurring must be 100%, right? If there's only 2 possible outcomes. For example, heads or tails. If I ask you, what's the probability of getting, if you flip a coin once, what's the probability of getting heads or tails? You say, well, 100% chance, right? I'm going to get one of those 2. So if there are 2 possible outcomes, the sum of those, the probabilities of those 2 outcomes must be equal to 1 or 100%, which makes sense. So if we say the probability of a single birth being a boy is 0.51, that must imply that the probability of a girl being a birth being a girl is 0.49. Why? Because their sum is 1. So how do we figure out 0.49? We subtract 0.51 from 1. If the 2 add up to, if these 2 numbers add up to 1, that means one of them is 1 minus the other one. And that's how you figure it out. So probability of a boy is 0.51. The probability of a girl is 1 minus 0.51, which is 0.49. That's only true if there's 2 outcomes. We can do that. Rule number 2. If 2 outcomes cannot happen simultaneously, like if we flip a coin, we either get heads or tails. You can't get both. They're said to be mutually exclusive. All right, fancy word for saying that the 2 outcomes can't occur at the same time. The probability of one or the other of the 2 mutually exclusive outcomes happening is the sum of their individual probabilities. Let me give you an example. If I roll a die, what's the probability of getting a 2 or a 3? Well, the probability of getting a 2 is 1 out of 6, isn't it? Because there's 6 possible outcomes, and one of those outcomes is a 2. So 1 divided by 6, or 1/6, is the probability of a 2. The same thing is true for a 3, right? There's only 1 3 out of the 6 possible outcomes. So 1 divided by 6 is the probability of getting a 3. So what's the probability of getting a 2 or a 3? Well, you can't get both of them on one roll of the die. You either get one or the other. So we add their probabilities, which would be 1/6 plus 1/6, which is equal to 2/6, or 1/3. Well, here's another example. If you think the probability of getting an A in your statistics course is 50%, and the probability of getting a B is 30%, then the probability of getting an A or a B is 80%. Now notice getting an A or a B has to be mutually exclusive, right? You don't get an A and a B for a course, you get an A or a B. So we simply add up their probabilities or percentages and we get 80%. So this is called the addition rule. of probability, and we use it when we use the word or. Notice it says, what's the probability of getting an A or a B? If you use the word or, we add. Okay, that's how you remember it. The word or means add. This is rule number 2. Here's another rule. This one is you have to distinguish this rule from number 2. If two outcomes or events do not influence each other, all right? And if knowledge about one does not help with the knowledge of the probability of the other, the events are said to be independent of each other. So we flip a coin 5 times. Each time we flip the coin, the knowledge of what the result was from the previous flip of the coin does not affect the probability of the current flip of the coin, right? Anytime we flip a coin, it's going to be a 1/2 probability of getting heads. It doesn't matter whether you got heads or tails the previous flip of the coin. So in that case, the different flips of the coin are considered to be independent of one another because the probability of one is not affected by the knowledge of what happened on the other event. So if two events are independent, the probability that they both happen, which means we can use the word and, then the probability of A happening and B happening, both happening, all right, independently of one another. It's found by multiplying their individual probabilities. So if we use the word and, all right, and, or but, or both, words like that that imply they're happening together, and we know that they're independent, we multiply their probabilities. This is called the multiplication rule. Here's an example. Woman has 2 children, will have 2 children, assuming that here, all right. Assume the outcome of the second birth is independent of the first birth, and the probability of that the birth is a boy is 0.51. What is the probability of a boy, the first birth? I'm going to rephrase it because this is bad English here. The probability that the first birth is a boy and the second birth is a girl is 0.51 times 0.49, which is 0.2499. So it's about a 25% chance a woman will have a boy and then followed by a girl. Okay. Notice we use the word and in here, right? Okay. Any questions about that? So we have 2 rules now, the addition rule and the multiplication rule. All right, let's look at rule number 4. If the ways in which one event can occur are a subset of those in which another event can occur, then the probability of the subset event cannot be higher or greater than the probability of the one for which it is a subset. All right, it's a little complicated the way it's written here. But really what it's saying is if you have an event and then you have an event which is a subset of that first event, the probability of that subset cannot be greater than the probability of the event itself, right? It makes sense. It's smaller probability. But what happens is people get confused when they see this situation and they tend to do the reverse. So let's look at an example. So suppose a person is 18 years old and is speculating about his or her future, and this person decides that the probability that you will eventually get married and have children is 75%. So the probability of getting married and having children is 75%. By rule 4, the probability that you will eventually get married is at least 75%. Okay. Can you explain why? Why does this probability of eventually getting married have to be at least 75%? Why does it have to be, why can't it be less than the probability of getting married and having children?
Is it because it can't be like lower than the subset?
What is the subset here?
That you'll get married and have children?
And why is it a subset? Give me the other possible subset. Remember, the event that we're looking at is getting married, right? And you're saying the subset is getting married and having children. What is the other subset? Because you should be able to tell me what the other subset is.
Is it getting married and not having children?
That's it. That's it. So there are two probabilities there, right? Right? So the probability of getting married must be at least 75% because it includes both events of getting married and having children plus getting married and not having children. Those are two mutually exclusive events, by the way, right? So if we said the probability of getting married and not having children is 0, because that's the lowest you can get, then 75 plus 0 is 75. But most likely the probability of getting married and not having children is going to be greater than 0. So that means the probability of getting married is the sum of the probability of getting married and having children plus the probability of getting married and not having children. It's going to most likely be greater than 75%. But most people, due to the way people's brains are wired, if you don't know this rule here, tend to give the answer that the probability of getting married and having children, they tend to have that, give that as a larger answer than the probability of just getting married. Okay, they tend to, because there's two things that are being addressed here, and they think, well, it must mean it's a greater probability because we're talking about marriage and children. But you realize now that it's a subset, it cannot be greater than the probability of just getting married. All right, and then we have this slide here, which does a little bit of the arithmetic behind independent events. Let's look at what this is saying here. All right, the probability an outcome will occur on any particular instance is p. So they're using a little bit of algebraic notation here, so you just have to bear with it. But we'll see an example of this in a second. So if p is the probability of something occurring, then the probability that it will not occur is 1 minus p. Remember, we talked about that. If there's two outcomes, possible outcomes, and the probability of one of them is p, we'll call it p, then the probability of the other one is 1 minus p because the sum of those have to be equal to 1. Now, if we consider each outcome to be independent of all the other outcomes, right, then it doesn't matter what the outcome of a particular repetition of the experiment is to determine the probability of the next one. That's what independent means. And so we use our multiplication rule. So let's look at, for example, rolling a die. And we want to know the event that we're interested in, the outcome that we're interested in is rolling a 3, as opposed to 1, 2, 4, 5, or 6, rolling a 3. So you're either going to roll a 3 or you're not going to roll a 3. So P in this case is 1 out of 6. That's the probability of rolling a 3. And the probability of not rolling a 3 is 5 over 6, because those are the other 5 possible outcomes. All right, so we're good with that. So P is 1 over 6, and then 1 minus P is 5 over 6. So suppose you roll a die once. So this is the number of repetitions here. You roll a die once, and let's say you get a 3 on the first try. All right, so the probability of getting the 3 on one roll of the die is what? 1 divided by 6, right? It's the P. Suppose that you did not roll a die, excuse me, you did not get a 3 on the first roll of the die, but you got it on the second roll of the die. That means it took 2 rolls of the die to get your 3. So the probability of that happening is 1 minus P, which is 5 divided by 6 times P, which is 1/6. So you multiply those two fractions. 3. Suppose the first 2 rolls of the die, you get something other than a 3, but the third roll you get your 3. So the first roll of the die, 5/6 probability because it's not a 3. Second roll, 5/6, it's not a 3. Third roll is a 3, so it would be 5/6 times 5/6 times 1/6. Get the idea how this works? Then what if it took 4 rolls of the die to get your 3? So the first 3 rolls, you did not get a 3, and the fourth roll you did. So we're taking 5/6 times 5/6 times 5/6 times 1/6. Okay. So this is the explanation of what this table was trying to tell you. All right. All right. And now we're looking at the number of births to get that first girl. All right. If we assume that it's independent of whether you get a boy or girl, if one birth is independent of another, right, doesn't influence whether the next birth is a boy or girl, then these are a list of probabilities of getting that first girl. Either you're going to get it on the first try or the second try. So if it's the second try, this is the probability of that happening. You have to consider what happened on the first try, which is the boy. It might take 3 births before we get our first girl. We have, in this case, 2 boys and a girl. This is the probability of getting 2 boys and a girl. It might take 5 births, hopefully not, right? But you might have to have 4 boys before you get a girl. So this is the probability of getting 4 boys and a girl. And then it might take 7 times. I don't know if anybody would be willing to do that. You know, we get 6 boys and then you get your first girl, and notice the probability of that. So again, this is the multiplication rule, right? We're saying what's the probability that it takes 7 times, which means the first birth is a boy, the second birth is the boy, and the third birth is the boy, like that. We're using the word and, so we're going to be multiplying, right? Multiplication rule. This is just an example of how to use the multiplication rule. That's really what they're doing here. Here's another example. Now, what they're showing here, what the term they're using in the book is accumulated probability, which means we're looking at a number of repetitions of the experiment and until the event that we're looking for occurs. So they're using formulas here to determine the end result, but you could use a table. My point is you could use a table. So if you're comfortable with these formulas, you may use them. Maybe most of you are not. You're looking at this and saying, what the heck is that? So let's look at an example and see how a table will be helpful here. Suppose the probability of an infection, an HIV infection, is 1 out of 500, all right? Which is 0.002. So, so these are sexual encounters, okay? I think that's what we're referring to here. So you have sexual encounters, unprotected, let's say, and you're looking at the probability of being infected with HIV. So on one encounter, the probability is 0.002. The probability of not being affected on one encounter, again, is 1 minus that, which is 0.998. So we might say, all right, well, if we had 2 encounters, what's the probability that we would get HIV on the second encounter? Well, it would be the first encounter, we did not get HIV, so it would be 0.998, but we did get HIV in the second encounter, which is 0.002. So we multiply those 2 numbers, and that is the probability of getting HIV on the second time. So they talk about accumulated probability here. This is sort of like a running total. So what you do is you take the previous probability and add the current probability. And so how do we interpret this 0.003996? That's the probability of getting HIV on the first or second encounter. Does that make sense? That's the addition rule. What's the probability of getting it on the first or the second encounter? It would be the probability of getting it on the first encounter plus the probability of getting it on the second encounter. These two numbers are added up, and we get 0.003996. That's what they mean by accumulated probability. What if we have 4 encounters before we get HIV? Well, the first 3 encounters we did not get HIV, so that's 0.998 cubed because there's 3 of them. And then the 4th encounter we got HIV, so that would be 0.002, and this is the probability of getting HIV on the 4th encounter. We might want to know what's the probability of getting HIV on the 4th encounter or less. Oh, sorry, or less, then we would add up the first 3 probabilities, and we would get, excuse me, the first 4. We would add up the 4th probability plus the other 3, and we would get this number here, 0.007976. All right, so a little complicated, but this is sort of how you read this table when you review it. Now, the other thing that probability is used for is what's called expected expectations, expected losses, expected gains. So here's an example. All right, an insurance company charges all customers $500 a year. All right, so they're charging everybody, whoever is a customer, this is their yearly, what we call premium. This is how much customer is charged. So all that money comes to whom? The insurance company. Insurance company gets this money. Now, the insurance says the following. It says, if a claim comes, and this is a very simple example, obviously insurance companies' claims are more complicated than this, but if somebody files a claim, they will be paid $1,500, just as long as it's a valid claim. The insurance company will pay the customer $1,500, okay? So any claim in a year will come to $1,500. We're assuming one claim on average could happen to a person in a year, maybe. All right, so how much can the company expect to earn or make per customer? So let's think about this for a moment. All right, now each person, each customer, $500, they're going to get money coming in. That's revenue, right? That's money coming in, $500. Now, suppose the probability of a claim being paid for any particular person is 10% probability. Why? Because it says 10% of the customers submit a claim in any given year. So we'll say the probability of a particular customer submitting a claim must be 0.1. Does that make sense? If 10% submit a claim, that means the probability that one person submits a claim is 10%, which is 0.1. So the probability that they don't, a randomly selected person does not submit a claim and get paid $1,500 is 90%. All right, so let's think about this for a moment. If a person submits a claim, they're going to get $1,500. Well, that person's already paid $500 to the insurance company. So that person actually gains $1,000. That does, right? Correct? They paid $1,500. Excuse me, they paid $500 and they gained $1,500 from the claim. That means they netted $1,500 minus $500 or $1,000. Does that make sense? On the other hand, if a person does not submit a claim, that person has paid $500. That's a loss. Now let's look at it from the perspective of the insurance company. The insurance company gets $500, but if they have to pay out $1,500, that means there's $1,000 they have to pay out. That's what the negative 1,000 here is. Negative 1,000 is the net. It's a loss for the insurance company for those people who they have to pay claims to, because they're getting $500, but they have to pay out $1,500. So they're losing $1,000 if a person gets a claim. But if a person does not have a claim, then they simply get the $500 from the customer and they don't have to pay anything out, right? There's no claim. That's where the positive 500 here is. So we have the probability that a claim is paid and a probability the claim is not paid. And we have the gains for the insurance company in each situation. They're going to lose $1,000 if they pay a claim. They're going to gain $500 if they do not pay a claim. So the question is, what is the average or expected gain for the insurance company? Now you hope it's going to be a positive amount per person, because if it isn't, the insurance company is stupid and they're going to go out of business. Make sense? It's always true. Any game or anything that involves probabilities, the person who is in business or the company that's in business, they better have an expected gain of a positive number. Because if they don't, they're out of business, ultimately. Like the casinos or the lotteries, they all have expected gains, which implies, by the way, that the individual who's on the opposite side of that transaction, like the customer here, must have expected losses. The opposite. Always true. Lotteries, casinos, all have expected losses for the people who play, but the casinos and the people running the lotteries, they're going to have expected gains. Well, what's the expected gain here? We expect a positive number. We take the probability and multiply it by the gain, 0.9 times 500. And then we take the other one, 0.1 times negative 1,000. Now they have minus here, but they really mean plus 0.1 times negative 1,000. All right. Hopefully you know that means the same thing. And when they add up these two numbers, they get $350. That's the average gain per person, per customer, per year. All right. So the insurance company has a chance at staying in business because this number is positive. If it's negative, they're stupid. They're going to go out of business. Eventually, they're going to go out of business. All right. Sorry about that. So, hold on a minute. There we go. So my question to you is, what is the expected loss per customer? How much is it? The expected loss per customer is the expected gain is $350 for the company. What's the expected loss? Assuming no profits. We're not dealing with any additional profits. What's the expected loss? Only one choice. It's $350. Doesn't that make sense? Where's the money is just moving from one entity to another. If the expected gain is $350 for the company, the expected loss per customer must be $350. Because if you add those two numbers up, it's zero. It's just money moving around. That's all it is. It's money moving around. Now, insurance companies typically pad this 350. They would probably charge more than 350 because they want to have a profit, an additional profit. So they might charge $500 per customer. All right, but this is how they figure out the minimum that they should be charging, $350. Or excuse me, they're charging $500, but I'm saying 350 is the minimum gain per customer. They have to have a gain for this arrangement to work. So expected value means that we take a look at all the possible outcomes and we add up the products of the values and their probabilities. We just add them up. That's what all the A's are all the possible amounts, and the P's are their corresponding probabilities. What are the possible amounts? That the company's either going to lose $1,000 per person, 10% chance of that happening, or they're going to gain $500 per person, a 90% chance of that happening. And they're simply multiplying the probability times each value and adding that up, and that gives you the expected value of the company's profit per customer. This expected value is the average value per measurement over the long run, and not necessarily a typical value for any one person or one occasion. So for a particular customer, it may be quite different, right? Because they may not file a claim at all. But this is basically over all customers over the long run, we would expect this result. This is how insurance companies determine how much to charge people. Okay. All right. So it looks like, by the way, we're probably going to get to some examples next time. We're not quite, I think we have how many more slides? A couple more. This is an example here of a lottery. Same type of idea here. All right. A player chooses one card from each of 4 suits, a winning card drawn from each suit. There's going to be a winning card from each suit. Prizes awarded based on the number of matches. Here's the cost. So, person playing this game is going to pay whoever is running the lottery $1. Okay. Here are the prizes. All right. If you happen to match 4 cards, you get $5,000. If 3 of the cards match, you get 50. 2 of the cards matching, $5. 1 card matching, you get a free ticket. You don't even get money. And no cards matching, you actually you lose the $1. All right, you're losing the $1. Okay. So basically, this is it. Now the free ticket means you're just getting another try at it, so there's no loss, right? You're going to try it again. And here are the probabilities of these happening. All right. These are the probabilities calculated ahead of time. Now we want to know what's the expected for a person playing this game. For a person playing this game, what is the expected gain? Now again, if you're a player, you should expect a loss overall. All right, doesn't mean you're going to lose. It just means overall, if you played this 1,000 times, you're going to lose. 1,000,000 times, you're going to lose. Now, how much on average are you going to lose? Well, if the prize is 500 and you pay $1, play the game, your net gain, if you win $5,000, your net gain is going to be $49.99, right? 5,000 minus the $1 that you played. You just subtract $1 from each of these results, and these are your net gains. And so you simply multiply each net gain by its probability. And then you add them up, and you see overall a net loss of 35 cents. So over many repetitions, players will lose an average 35 cents per each time that they play this game. What does that mean? Well, if it's $1 to play the game, right? $1, okay, then the lottery commission will only have to pay out 65 cents for each $1 ticket sold. Does that make sense? Because they're going to gain 35 cents. So the lottery commission will gain 35 cents on average each time a person plays, which means on average they're going to be paying out for each $1 they sell, they're going to pay out 65 cents. 1 minus 65 cents is 35 cents. This is how lotteries work. All right. So in measurement taken over a large group of individuals, the expected value can be interpreted as the mean value per person. Well, another way of saying it is average value, the average. All right. So expected value and average tend to mean the same thing. Suppose 40% of the people in the population smoke a pack of cigarettes a day, and the remaining 60% don't. What's the average number of cigarettes smoked per day by each person? Well, if 40% of people smoke, and 60%, that means 60% don't. And if 40% smoke a pack, which is 20 cigarettes, so 40% times 20, and then 60% times 0. So obviously this is not very realistic, right? Because most people, they are smokers, they would smoke a different number than 20. But we're looking at these 2 possible outcomes. Either you smoke and you smoke 20 cigarettes, or you don't smoke and you don't smoke any. What is the expected number of cigarettes smoked per person? 8. 40% times 20 is 5. Is 8. 60% of 0 is 0. So 8 cigarettes on average. The long-term expected number of cigarettes smoked. All right. All right, any questions about that? We'll skip this last example. We have all of these notations here if you're interested. You don't need them for this course, but if you're taking a statistics course, you would probably need to know what you're looking at here. Any questions? We've got about 4 minutes. Let me take a quick look at the problems that I have looked at the back of chapter 14. Share that screen here. So this is posted, and on page 323 to 326, we have several problems here, and they're all odd numbers so that you can look them up, look up the answers, okay? But this is the solutions here for that. And for number 9, for example, there's 2 different scenarios that are offered there, and they're asking you whether it's the relative frequency approach or the personal probability approach that's being used for the probabilities. So I think you should be able to look at that, read it, and be able to figure that out. If it's, if the person's running a long-term experiment, or are they just guessing at it? All right, number 11 is maybe we'll take a look at it next time because this will take a few minutes to go over. And so there's 2 parts of that. And number 12, which you don't have solutions to, also we'll look at next time. So we'll take about 10 minutes next time to go over these problems at the back of this chapter, and then we'll go right into chapters 16 and 17. We're going to do 2 of them next time. And then number 14, yeah, I guess we'll need to go over these. These are all examples of what we covered today. So we're running out of time. We only have, I think, a minute left. Any questions about what I covered today? Again, I would highly recommend, when I mean highly, I mean strongly recommend that you read this chapter. This is one chapter I think you should read and follow along with the examples. And then these problems, again, I'll review with you next time for the first 10 minutes or so. I do want you to try these on your own, so I'm not going to be spending, half hour, 40 minutes on this. I'm going to go through, we'll read through the problem and go through, in general, how to solve it. But what I want you to do is try these problems on your own without looking at the solutions. All right. So, next time, after next meeting, that's what I want you to do. I want you to try these on your own. You may struggle a little bit, that's fine. And then you'll look at the solutions. All right. So please don't just think that the solutions here, I don't need to do anything. No, you should try this. This is how you learn with math and statistics, is you need to try things first. Don't get frustrated if you're having trouble, and then look at how it's done in the solutions here. All right, so that's it for today. Any questions?
Will
No?
the quiz on Tuesday be just around chapter 14?
No, 14, 16, and 17.
All right, thank you.
Yeah, we're covering all 3 of them this week. All right, so that's it for today. So I'll